Nowadays, we are developing the machines such that you can control the machines by sitting in your home and you can develop the required products. That is a autonomous machines are coming into the picture soon. I think 2 days back in Hindu paper, I read that one doctor is conducted the operation 9,000 kilometers away from the operation theater. 9,000 kilometers away from the operation theater, and he just succeeded. So similarly, nowadays when machines are coming, we can operate the machine, even you can sit here and you can operate the machine in the USA also. So like that, so many challenges are coming into the manufacturing and the material science, and there is a cooperation required between the manufacturing engineering and materials manufacturing engineering and materials engineering. I hope that this conference build a network between the material engineering and manufacturing engineering, and it will be helpful to accelerate their research in their respective fields. I hope that you can enjoy today's keynote speech as well as this today's conference, and you can enjoy this one and you enhance your skills. Thank you. Thank you.
Thank you, sir. May I now request our HOD EEE department, Professor Ashok Kumar sir, to please join the dais. Thank you, sir. I would like to request Conference Co-Chair Professor M. Venkateshwar Reddy sir, HOD Mechanical Engineering, to address the audience.
Good morning, everyone. Respected dignitaries on the dais, Principal Sir, Dr. K. Srinivasa Garu, our Vice Principal and IPSC Head, Dr. Icasmmt Ma'am, and our General Chair, Satyanarayana Gupta Garu, and respected other head of the departments, and special thanks to all management, Sri Lakshman Reddy Garu, Chairman, and our Secretary Rajshekar Reddy Sir, and the Directors Kiran Reddy, Shaya Reddy, and as well Mamta Reddy, to getting this first international conference by Mechanical Department a successful event by organizing all the things for us. And special thanks to our convener Balram sir and our faculty who are worked very hard from last 2-3 months to get the papers as well as scrutiny and finalizing the papers and making this event a grand success. And it's a very proud moment for all our students, members, and our participants also. Thank you very much. And here, the sustainable energy and materials manufacturing plays very important role in the development of the society. Because everyone, even we are going to space, means just not for tourism. Okay, it's just not for passion. Okay, it's because of getting the new materials, lightweight materials, improving the efficiency, okay, making the new products. Many researches are going on like that. Not only we are going in automation orientation, we are always going with lightweight concept and other technologies. So mechanical engineering always plays very, very important role. Okay, it will be there for ever because world cannot move without mechanical engineering. Okay, this thing you need to raise on this. Okay, and another one is either it is artificial intelligence, either it is any other advanced technologies like robotics. Okay, everything the base is from the core branches that we need to concentrate. There is more scope on the research. Okay, because wherever you go for the defense sector or either is R&D and all, it starts from the core branches like mechanical engineering, metallurgical engineering, aerospace engineering, then after that chemical engineering. Okay, then we can move to electrical, electronics, civil and all. Okay, so here is the need of research always. because as a students, we need to just not doing the jobs and just to make the products is not our only motto. We need to go with the research hands to hands to make ourselves more comfortable and to give them more easiness to do the works, because tomorrow the industry come up with the autonomous vehicles. Okay, no need to call any driver. Okay, the car will come and pick up you and it will arrange everything for you. These technologies hand to hand with computing like and coding, we can make together can make wonderful products, which will help us a lot. And the another area is to encourage the research area. We are regularly making the conferences by the various departments. Of course, we completed 6 Icasmmt, which are successful. Maybe that is the base. Because of that only we got, even if this first time, we got huge response. Thanks to Gupta sir, because that the base he created for us already. That is the response came. Really, we are also not expected 380 plus papers. We thought of 200 plus will be a good achievement. Really, it's a very great situation for us to complete 20 papers accepted in this conference. Okay. Thank you one and all, because here everyone helped us, not only our faculty, all other departments and other college faculty and scientists, and many people are helped to make this success. And even our Vijay sir also one of the key factors. Thank you everyone. It is helpful.
Thank you, sir. May I now request Dean IQAC, Dr. Radhika Devi ma'am, to please speak a few words.
Thank you, Akshaya. Respected Principal Sir, Convener, General Chair, Co-Chair, the Director, Chair, Patron, and Chief Patron for the conference, also the Controller of Examinations and the heads of the various departments, faculty from other colleges, my dear students. Once again, a very warm welcome to this first international conference on advancements in sustainable energy, materials and manufacturing technology. So as already briefed by Gupta sir and Venkateshwar Reddy sir, I'm not going to speak anything on what materials are or what sustainability issues are. But what I like is the Mega has come as a competition for the anchors. So this is what is going to happen in the next few years. That of course it's not a threat basically, that whatever we do can be done by these machines also by some little amount of perfection. So when Megha was speaking, I was trying to look at how it is speaking and how she is speaking and with what perfection she is doing things and what we have to learn from that. So one beautiful thing that all the students over here must understand is, it's a very beautiful opportunity for you all people that in the place where you are sitting, which means in the college itself, you are having this international conference hosted by us. You please have to take this opportunity to the fullest extent, not just to make it a successful one, but to make yourself successful in understanding like what research is going about. Because if you go back some 10 to 15 years back, we had to travel to some other institutes in order to attend the conference, in order to listen to the keynote speakers. But for you people, as I mentioned, wherever you are sitting, you are having all the facilities available. So listen to the keynote speaker, understand things, and also my sincere suggestion is that if you can sit in the paper presentation sessions, you will also understand what research is going on, and your ideas will also improve that. Okay, this subject is where I have to concentrate, and this is the area where we can start doing research. As mentioned by Venkateshwar Reddy sir, mother of engineering is all mechanical engineering. So it all starts with materials, and then as Gupta sir mentioned, the dosti between manufacturing and materials. It will be there, dosti forever. So understand this important aspect when you are listening to everybody, all the speakers, all the papers that are getting published, in which direction the world is moving. right? And you people also start working in this direction to publish some papers, and this is where your journey towards success will start. So I really congratulate the department for organizing such a wonderful event for the department as well as for the students. Thank you. Thank you for giving me this opportunity.
Thank you, ma'am. Now I request the conference chair, Dr. K. Srinivas Rao sir, to address the gathering.
Radhika ma'am and heads of the departments, Gupta sir, Mlrit Reddy sir, Chiranjeevi sir, Ashok, Mlrit Reddy sir, and Prabhakar. And my dear faculty, students, and the scholars who are there on online, those who are listening to it and those who are viewing, because it is already aired in YouTube. So my sincere appreciation. Hello. My sincere appreciation to the Department of Mechanical Engineering for organizing such a wonderful conference on sustainable energy, materials and manufacturing. And yes. Hello. Is that fine? Or you give me that another piece? Right? Yes. So my sincere appreciation to the Karthik and team for Meta. So give a big round of applause to them. So they have beautifully demonstrated how the robot will work. I think they have worked for around 2 months to 3 months, very focusedly, very sincerely on that. And every aspect of it, I know it, and how we can train even machine also. They have demonstrated that the Mlrit students can train the machines. Yes or no? Yes. So they are the witness. Coming to the conference, I'll touch upon certain sustainability, renewable energy and other things. Before that, you're all the students of second year, third year and first year. So try to understand, though you are in a mechanical engineering, you have limitless opportunities in every area. So you can develop a machine like it, no need to go for a CSE to develop this. Only the willpower is required. How it will work, and what we need to do it to make this, right? So it need not be a mechanical engineer, and it need not be a CSE, and it need not be an electrical engineer. Only the willingness to do it that will help you to grow. And the order of the day is now the multidisciplinary of engineering. Multidisciplinary of engineering means where so almost they have given it mechanical engineering students, electronics, and even computer science students, right? So it is only the thing is, so finally no, willingness to do it, willingness to work, that's it. Coming to the conferences of such kind of things as a student, so try to learn from the people here. Maybe in another 5-10 minutes, keynote speaker will come and will address you on 3D printing, materials and manufacturing. So not only that, tomorrow also there are the certain keynote addresses. So try to listen to it and try to adopt the things that they are trying to deliver. Around 300 and plus papers are received on this particular area. So I congratulate the convener and the Department of Mechanical Engineering for their wonderful efforts. And I'll touch upon certain things on sustainable energy. So sustainability in energy, materials and manufacturing. Sustainability is not just a buzzword, it is a responsibility that we as global citizens and academicians must uphold. The rapid pace of industrial development, while necessary for progress, must be aligned with the principles of environmental stewardship and resource conservation. This conference is a testament to the growing awareness of these challenges and the need for innovative approaches in sustainable energy, advanced materials, and manufacturing processes. The global energy crisis, depletion of natural resources, and the impacts of climate change demand that we rethink our strategies. It is heartening to see how researchers, engineers, and scientists are stepping up with breakthroughs in renewable energy, green materials, and eco-friendly manufacturing technologies. The work all the researchers and participants is doing, and they are shaping up the industries, but also improving the quality of life for future generations. The role of academic and research conferences like these play a vital role in fostering collaboration between academic, industry, and policymakers. As an educational institution, MLR Institute of Technology is committed to creating platforms that encourage knowledge exchange, innovation, and interdisciplinary research. Our students, who are the future scientists and engineers, are inspired by these cutting-edge technologies. So what this conference is bringing to you. We believe that sustainable development is only achievable when we are open to new ideas, research, and partnerships that transcend the borders. This conference provides the perfect environment for these exchanges, and I encourage all of you to engage with one another, ask questions, and collaborate in the spirit of shared learning progress. As we embark on this intellectual journey over the next 2 days, so let us remain committed to the goals of the same: sustainable energy, materials, and manufacturing, and responsible development of the nature. I am certain that these ideas, the papers that are going to deliberate, the solutions generated here will have lasting impact on both academic research and industrial applications. I wish you all the best to the Department of Mechanical Engineering and the students and participants who are joining for this international conference. Thank you.
Thank you, sir. It is our privilege to welcome Professor Aman Kumar Gupta, sir, a renowned expert in mechanical engineering from BITS Pilani, Hyderabad. We request you to please join us on the dais. I also request Dr. Jaiprakash Sharma Panchagmula, sir, to please accompany. Thank you, sir.
I was requesting sir to address.
We please request Professor Aman Kumar Gupta, sir, to please address the gathering. It is with great honor and immense pleasure as we gather to celebrate a momentous occasion.
We now invite all our distinguished guests to join us for the official launch of conference proceedings.
Thank you, everyone. We are excited to announce the launch of our upcoming conference, Icasmmt 2025, the second international conference on advancements in sustainable energy, materials and manufacturing technology, organized by Department of Mechanical Engineering, tentatively on March 21st and 22nd at Mlrit.
And volunteers.
Thank you, everyone. May I kindly request all the dignitaries, organizers, and volunteers to please come forward for a group picture.
Also participants. Also participants.
We also request the participants to come onto the dais for the picture.
Volunteers and చెప్తే ఎవరు వస్తలేరు సార్.
We request the volunteers also to please come forward.
ఇంకెవరితో people moving inside.
Thank you, everyone.
Sir,
Sir.
keynote speaker profile చెప్పి రమ్మని చెప్పు.
Keynote section will start. Please, can you give Please.
We now request our keynote speaker, Professor Amit Kumar Gupta sir, to please take over the session.
Good morning, everyone. Good morning, all the college authorities, conference organizers, and all faculty and all students and staff. Thank you for organizing this conference. Generally, I say in my own place that organizing conferences takes a lot of effort. And so, congratulations to all the organizers. Not an easy event. I once again heartily appreciate your efforts to organize this conference. So, I have played this. I'll operate on this. This is giving echo. Okay. Thank you. Thank you.
Also, just maintain a bit distance.
Okay. Yeah, because this is too much. Thank you. Okay. Is it better? Clarity? No. Now? Not at all. You want to switch it off? Is it better? Better? No.
Hello.
Okay. I hope this is clear, audible. Thank you. So, So first of all, I appreciate the efforts taken. Okay. appreciate the efforts taken to organize this conference. So this conference is about sustainability, materials and manufacturing. So this talk is about something called smart materials, which hope it will give a tinkering to you that there are such materials which exist and there's a lot of scope to do research and development in these materials.
We wanted to stay very close to the mic, sir, else you have to.
Okay, then leave it and use it this one. Okay, sorry, I have turned it back on this. Generally, that is too constrained to stand in one place and speak. I keep moving. I am not treating it as a conference talk. I am treating it as if you are my own beta experts, and I am just delivering a normal lecture to you. Hope you won't mind it. And as team faculty members, you take it as someone who has come with little knowledge. You can give your inputs on this. So, this talking about shape memory alloys, technologies and applications. One thing before I start, I'll tell you that I am also new to this field. Okay, just to give you confidence that anybody is entering very deep and can get into it. At a student level, at a faculty level, or even a senior faculty level, you can start any new field at any time.
Sir, put it a bit.
Okay, thank you. So, my actual PhD was in, just to give you a little bit that personal touch, my PhD was in scheduling, in industrial engineering. But after moving back to India, I found there is better scope in materials. So I shifted my research field to first to materials, and then to smart materials, and then to shape materials. So that's where I just want to give you that there is nothing called expertise in research. You always have a beginning. In fact, as a teacher and a researcher, you always have to be a learner. So I am presenting this talk as a learner, not as an expert. So I raise my hands. I am not an expert. Now you can question me anything. If I know, I'll tell. If I don't know, I'll tell. I'll together we'll research about it. So with this, I'll start the talk. This is about shape memory alloys. Just before that, Pilani has 5 campuses in India. 4 in India, 1 in Dubai, 1 is missing here. This is an institute of engineers, and we take our friends from exam. Next, please. So, this is just a content. I will not follow exact same style. This is about launching of a satellite. Both of them done with mechanical impact, aerodynamic and non-explosive. And then moving on to assembly-based devices, shape memory alloys, and then concluding with the smart materials, which may be actually something which you may explore in the future. Next, please. So this is launching of a satellite. Launch satellites deployment in the orbit is a big challenge. It's not a small thing, and India is developing fast in that. ISRO is now leading in the world. And just think about it. Can you play the video? The first video. Okay, fine. So this video can play. Think about it that you have satellite folded into a small space, and it has to go with a high speed. And after reaching to the orbit, it has to be deployed there. It has to be open. So you need to have something to hold it tightly when you need it, and something to release it when you need it. So that's called hold down release mechanic. Now these devices are actually explosive based. Now you can think of explosion. When explosion takes place, high shock wave comes. And electronics are very sensitive to shock waves. If something goes wrong in the electronics, your whole mission is a flop. And actually it happened many times. These missions flop due to failure of these devices. So the focus here is just one application of shape memory alloys. Next slide, please. Video. So this is satellite launching. You can see your antennas and other panels, solar panels are hiding there. Big, this thing, that's a small thing which you are sending it in an orbit. It goes up, short waves are there, high voltages are there, and then it takes its own path, finally gets into the orbit, and then it's deployed. High vibrations are there, and under those, your electronics, your hold down capacity, releasing it is not an easy task, it's a challenge. Next slide. Next. Yeah. So, the need of hold down release mechanism is to be able to tightly hold the satellite into the folded position in the deployment, and it should be able to unfold the satellite at the time of deployment within the time frame and with ease and reliability. This is important time frame. Just think about it. Milliseconds, you are off the orbit. You leave it milliseconds before, you are not in your right place. You want to have a satellite over India, but if you are not putting in the right orbit, after 2 months it will be over Pakistan or some other country. This is another example. So it needs very high precision at what time it releases it, when it reaches the orbit. So for that purpose, these devices have to be very precise. And they are in nature two types: one is pyrotechnic based, another is non-explosive. So in pyrotechnic, I will not get into detail of this slide, but pyrotechnic is something like this. This is gold, and you have an explosive on the top, and with that explosive, here at this point, it breaks. Simple mechanism, but it gives a lot of shocks to the whole system. The alternative to that is doing research. The alternative to that is, let me just, you want to show it to you? So the non-explosive type, where we release it based on the action of shape memory alloy. What is shape memory alloy? That will cover after 5-10 minutes. So this is a small current being passed, and based on that current, our shape memory alloy activates and it gives release capacity to the mechanism and it releases. So that's your shape memory wire, which is grounded up, and that's your exactly holding device. So when you have actuation, this is the full mechanism right now. So these balls, if you see, they are not in the socket. Once they come in the socket, it will get released. So you pass the current in it, and then because of that current, this wire gets loosened, and because of that, this whole mechanism falls off. And these devices are actually used for even multi-stage separation mechanism also, because many satellites has to be launched in 2 or 3 stages. So there also they are useful. Next slide. Next one. Just skip. Next. Next, maybe this one also. Next. Yeah. So the basic mechanism goes here as this, that you have something called output pin, and you have SMA wire, and there is a drive spring, and there is a ball mechanism. Many of you may not see this picture, but this is a ball on which it is holding. And when you activate the SMA wire, it gets pulled up, this ball falls here in this socket, and then it gets released. So it's a matter of milliseconds that you have to activate it. You give a command, within 200 milliseconds it has to activate. That's the precision we require. And similar devices are required even for launching missiles. So that's the high scope in aerospace and defense both. Next slide. So this is simple, again a video. How does this work? So that's your whole mechanism set to installation phase. That's your pin outside, which is hanging the load. So when you activate it, this pin simply gets retracted and your load falls down. That's how it works. So a lot of US companies are working on these devices. NASA actually uses non-explosive devices for these purposes. India still uses explosives. Next. Next. Yeah. So now let's get into what is materials behind it, what we are trying to talk about today, shape memory alloys. So I'm sure you have heard about
not shape memory alloys, many of you may not have heard, but at least you have heard about shape memory foams, matrices. What does shape memory mean? Any volunteer? What does shape memory mean? From matrices perspective, not from alloys perspective. So I assume that all of you sleep on the hard bed, you don't use mattresses. Traditional old Indian style. No. Please tell, anyone volunteer? What is shape memory? Yes. It regains its shape. Which shape? Thank you. I want you to participation. Otherwise, it's a monologue, it's a boring thing for me and for you as well. So, shape memory, as the word says, is a shape is being and by the alloys. That's something interesting. An alloy can remember the shape. What shape you train, that shape it will remember, and when you want to actuate it, it will give you that shape. Something interesting, has a lot of applications. Okay, I'll give you those applications a little later. Let's first understand the material. So this material which remembers its original cold forged shape, and by heating it returns back to the redeformed shape. That's the shape memory alloy. SMAs are materials which can revert back to original shape and size on cooling by undergoing phase transformation. So this part we need to get into little metallurgy, that there are two kinds of phases in this metal. This is one example of this is nitinol, which is thermal based, and another terphenol D, which is magnetic shape memory alloy. So when we say thermal, that means we heat it up, it will gain its V shape. Magnetic means you apply magnetic field, it will gain its original shape. That's the part of it. Now, it was actually developed by Naval Ordnance Lab in 1953-63, where we had 55% nickel and 45% titanium by atomic percentage. By weight it will be 50-50. So we call it nitty 50-50. This alloy is very light, lighter than titanium total. So this aerospace material. First it was developed in Naval Ordnance Lab, so we still call it as nitty plus nol, NOL. Nitinol is a famous name for it. One excellent part of it is this. Let me ask you back that question. For normal steels, aluminium, all these materials, alloys, what is your elastic limit? How much percentage elongation can take up to elasticity? Answer is there. If you can want to look at that. 0.2%. 0.2% is the elasticity limit. Beyond that, it has plastic deformation. You cannot regain the shape. But this alloy has elasticity up to 8%. Can you think of 8% compared to 0.2%? That's the unique part of these shape memory alloys. And to your surprise, first actually it was developed in a combination with gold cadmium alloy. Scientists were working on gold and cadmium alloy combination where they found this phenomenon. Then later on they developed nitty combinations. So there are various examples: copper, zinc, nickel, titanium, gold, cadmium, etc. Next. Just some physical properties. Melting point is somewhere 1300 degrees Celsius. Good prospective candidate for aerospace. Density only 6.5 gram per centimeter cube, and so on. UTS is 1100 compared to titanium. So much better than steel. So it is a good candidate, much better than aluminium. Next. Yeah, this graph is important. This talks about two phenomena in these materials. One is shape memory property effect. Another is called shape super elasticity. So if you think about it, you have seen the materials. You have a box. So you have wires, like you have steel wire, aluminum wire. You have the wire, you strain it, and beyond 0.2%, if you strain it, it doesn't come back. It retains that shape. This alloy can come back. More than that, so this is your wire. You may not be able to see it, but just showing you. This is nitinol wire. So if you elongate it somewhere 6%, That means you got permanent deformation in it. And after that, you supply heat to it, equivalent to 80 degrees Celsius. 80 degrees Celsius is nothing but hot water. So if you deform it, put in the hot water, it will regain its shape. That's the fantastic property of this. That's this curve, first shape memory effect. You load it, you will unload it, you will get some deformation in it, and that deformation can be reverted back if you supply heat to it. How to supply heat? Resistance heating or any medium heating, either air or water. We'll show you some demonstration at the end. The second quality is super elasticity, where we said that 8% elasticity is there in this material. You can stretch it till 8%, you leave it, it will come back. So this wire, if you see, if I hold it like this, it will not form this shape, it will come back. That's the property of this material, shape memory effect and super elasticity. Next. Same in a different way, 3D picture. There are 3 axes, stress, strain and temperature. Next. Quickly going through this metallurgy part, there are 2 phases, Martensite phase and austenite phase. Martensite phase is below 15 degrees Celsius, 25 degrees Celsius depending on your material combination, and austenite phase is above 50 to 60 degrees Celsius. So beyond 50 to 60 degrees Celsius it behaves one way, below 25 degrees Celsius it behaves another way. So that's how you remember the shape of the object you make. Next. Now programming of nitinol. Now if you see, there is a star shape. So you have, how do we set it? Shape setting is I will say science plus art in it. You have to have fixture. In that fixture you tighten it and then you put in a furnace somewhere 500 degrees Celsius for around 10 minutes. Then whatever shape you get, that's your actual shape. Now I'll just give it a small demonstration. What do you see here? You can't see anything. Maybe I should give you a white surface. Can you see something now? This is okay. This is spring, right? This is spring. If I pull it, you can see now it got deformed. Now it cannot come back, right? Now he's my PhD student. He's helping me in all this. This is hot water. I hope it is sufficiently hot. No, it became cool. Maybe you make it ready. We'll show it little later. So, go to next slide. So what happens? When you deform it, initially it was in twinned martensite phase. When you deform it, it goes to detwinned martensite. When you heat it up, it goes to austenite. When you cool it down, it comes back to detwinned martensite. And that's where you have this phenomena called shape memory effect. Next. So these are few same demonstration which I wanted to show you. Just can you play the video? So that's how you have the wire. Shape is set in a unique form, and if you see now, we are just going to put it in hot water. This is a hot air gun. First with the hot air gun, it immediately comes back to original shape. Again we deformed it and you put in hot water. See the actuation time, how much time it takes to get it to original shape. Okay, that's the part of this material. Again, this, have you seen this kind of wheels? Mars rover. Okay, this was used in Mars rover, this wheel by NASA. And if you see, if you have any ordinary wheel, if it goes to this terrain, either the wheel will spoil or your vehicle will not move. But because of the super elasticity of your material, of your wires, worn in that way, it will regain its wire strength, wheel strength. So that's the application of SMA. Next. applications of SMA in terms of biomedical, in terms of automotive, structure, important thing. The structures, like Japan of countries, they use this. Japan is an earthquake prone region. Lots of earthquake comes. And because of that, buildings are not stable. So if you have an earthquake and this building gets shakes like this, what will happen? Some crack will come, some building instability will come. So what they do? They put the shape memory alloy, either the road or the bars, they put in this material. So if the crack came in the steel structure, steel or your cement structure, but there is assembly element in it. So what you do? Assembly element got deformed along with the concrete. You heat it up, assembly element, it will go back to its original shape, it will fill the crack. So that kind of application in structures, bridges, and then you have suits made out of fabric where you want to maintain a shape. You loosen it and then heat it up, you will gain the shape. And so many examples in terms of aerospace. Next. Okay. So you brought the hot water. Thank you. You can see this now. This is your spring. Got deformed badly. Now it is no more a spring. But now I'll just put it in hot water. Actuation time, very fast. This was your original spring. Okay. Any volunteer to try it on your own? One volunteer? Come. Good. What's your name? Vinay Teja. Okay. Deform it the way you want to deform. Yes. So first pull it as much as you want. He is really hard guy. थोड़ा मर्सी दिखाओ भैया उसको. So this came back to the original shape. Somewhere he led to more than 8%. That 8% will not come back. Within 8% it will come back. Okay, don't try again. Okay, thank you. This is yours. Now, there are lots of applications. Smart switches, safety devices, artificial limbs, blood vessels, adhesive tape, food packaging. I will get into the detail of it in the interest of time. Smart clothes. This example you are seeing, lifting a muscle wire. This is an interesting example. Robotic hand. Now, many times soft robotics, what we call. Doctors use heart operations, artificial hands. So for that purpose, you have, if you see in this, it's all soft material. In that you have native wire, and you can do your design of your circuitry in such a way that whichever movement you want, it will have. Once you want to pick up something, it will be like this, and then you release it. So even for radioactive materials, you don't want to touch it on your own. For that applications also, this is useful. Next. Now, switching to little smart materials, this was, SMA is one of the smart materials. There are lots of other smart materials. Not to get into detail, but just give you a glimpse. These materials, smart materials, are in the category of materials which can think on their own. They have the mental alertness, quick perception, speedy activity, etc. They can respond to receive information, or analyze and decide, or act on a decision. That's the power of your material. Okay. Next. Yeah, one little go back. Once back. Yeah. So smart materials are sensitive to, so some materials are depending on stress. When critical stress develops, they actuate, or temperature, or moisture, or pH, or electric and magnetic fields. There are different variety of smart materials which behave as per these stimuli. Next. This is just to give you one by one. So they respond in real time. Like, you got a shock, you immediately remove your hand. Next, transiency. That it's a phenomena wherever you are, it will show the effect there. You move out, it will not show. So that's your directiveness. Next. So they change their property under different stimuli. One example, few examples, one by one. This is thermochromic. That means you have thermochromic, thermal plus color. So you provide heat to it, it will change its color. You might have seen many such mugs. Hot liquid you pour in it, it changes the color. That's thermochromic. Next, your magneto-rheological. This is interesting. Rheological means you have, as you apply magnetic field, it changes its property and it becomes liquid to solid. You can pick it up. That's your magneto-rheological. Next, thermotropic. With thermal heat again, it changes. Next, shape memory. So that's a tower and you have trained it in it that you bend it and then again you can unfold it based on heat. Next, these are energy changing, these are shape changing, these are energy changing. Piezoelectric. I am sure you know piezoelectric materials, that they have electrical plus stress. You provide stress, you get electricity. You provide electricity, you get stress. That kind of a conversion between the two. Then thermoelectric, you know about it. This is quite common in the 11th, 12th class. Photovoltaics. Then electrostrictive. That means you have two different materials and based on that you can actually develop photoluminescent. Next. So that's the classification of smart materials based on application, structural, electrical, biocompatible, etc. And then based on your actuations way. Next. So that's about a short talk on shape memory alloys, materials for future defense and aerospace applications. Thank you. Now I request a continuation of this talk by my colleague Dr. Jayaprakash on additive manufacturing, which is another interesting area for mechanical engineers.
Yeah. Yeah, good afternoon everyone. Thank you for inviting me for giving your talk on, I will not be talking much on additive manufacturing, but I will try to give you a small introduction on additive manufacturing. So as I feel it's somewhat related to the conference because it's on materials as well as manufacturing. So myself, I'm Dr. Jayaprakash. I'm presently working as a faculty in BITS Pilani campus, but stationed at Hyderabad campus. So, my talk would be like I'll try to give you a small introduction on additive manufacturing, and then I'll try to give you what is additive manufacturing and how many types of additive manufacturing, what are the advantages, limitations, what would be the future, and what are the actual needs for the additive manufacturing. So so before going to additive manufacturing, let me start with manufacturing and then we'll move on to the additive manufacturing. Most of the cases in mechanical engineering or any engineering perspective, if you look at any metal component, there are 4 ways of manufacturing in conventional. We all know the 4 types of manufacturing: casting, material removal, joining operations and forming operations. This is one way of doing, but most of the cases material removal operation or subtractive manufacturing is very much related with the industrial level components. In the other way, we can also manufacture a component using additive manufacturing technology. So, please, next slide. So, in conventional general manufacturing, also subtractive manufacturing, we might be talking about the conventional manufacturing process, 4 ways of manufacturing, and there will be multiple sub-classifications under it. So, at the same time, the industry's requirements as well as the present level of technology is at a higher stage, that wherever we are getting the regular surface finish or the dimensional accuracy, we may not be able to get it with the conventional. In such situations, or in some specific requirements, we can also go for the non-conventional based additive manufacturing process, such as laser welding, laser cutting, water jet cutting, abrasive jet cutting, electrochemical machining, electric discharge machining. Those are all non-conventional. As it's a textbook language, but it's no more a non-conventional. 20-30 years back, those already manufactured and they started using in industries. Initial days of manufacturing, they used to say it's a non-conventional, but nowadays it has become also a conventional manufacturing technique. So, if you are talking about manufacturing, the basic definition is, if you go to any manufacturing process, I have a raw material, I want to convert a raw material into a there might be multiple ways of manufacturing a component. See, if I want to manufacture a simple cylinder, I can do it by casting, I can do it by forging operation, I can also do it by powder metallurgy technology, same material removal operation, multiple ways. So, but the definition basically, I will be converting a raw material into a finished good. That is what the basic definition for the additive manufacturing. So, not additive manufacturing, regular conventional manufacturing process. So, this is not only a process of just converting a raw material into a finished good. There would be another thing, that if I give you a 1 kg of iron, what would be the use of it? A raw material of 1 kg of iron. Unless until it is a paperweight, there is no use of it. So, if I convert a raw material into a finished good, then its value is going to be added to it. So, we can also say manufacturing process is a value addition process. It's a value addition process. See, for an example, the same. What would be the price of 1 kg of raw iron? Any idea, anybody? 1 kg would be around 40-50 rupees, right? Regular raw iron material. So, but with that iron, if I try to manufacture bolts, maybe 20 bolts of M10, then each bolt would be of 10 rupees. Then from 1 kg, I will be converting it into some value addition to it. So, manufacturing is also not only just a conversion of raw material into a finished good, it's also a value addition process. As I told, there are multiple ways of manufacturing it. So, casting you can do fabrication, means joining operations, forming operations like deformation operations, like that in multiple ways we can do it. That is the basic. See, you just take any metal component, either in these 4 technologies they will be manufacturing it. You take anything. So either it might be a forming operations or casting operation or material removal operation or material joining operation. May not be a single operation, but there might be multiple sub joinings or sub process will also be there. So combination of multiple process will give you a final component. But if we are talking about the additive manufacturing, but this is something different. So why we are having only four classifications in conventional manufacturing? Because those are all the only ways of doing it. Only ways of doing it. Okay. Before going to additive manufacturing, I would like to ask a simple question, and then so whatever the plan they give it to me, I'll give it to them if they answer. Can you guess the age of casting process? How many years old it was? Any idea? Casting? 1500. Not exactly. Any? 400? 4000? 3000? No. Any idea? When was casting was invented? First casting. Any idea? Don't Google it. If you Google, then
7,000.
yeah, that's a precise answer. 7000 is the correct answer. It's a 5000 BC. Before Christ, 5000 years the casting was. So after death, we have 2000 years here. So close to 7000 years. So similarly, all conventional manufacturing techniques are having its own history of more than 100 years, 200 years. But the additive manufacturing, can you guess when additive manufacturing was invented? It was invented in the year of 1986, and the first additive manufacturing machine was supplied to available in the market in the year of 1987. It's around 35-36 years old. That's it. Just 35 years. So I can say, compared with conventional manufacturing, additive manufacturing is in a nascent stage. It's an infant stage, I can say. But we can do wonders with additive manufacturing because of its advantages. One point that I would like to keep, I want you to remember that the first additive manufacturing process, which was developed by Professor Charles Hull from Texas University, and there were some other collaborators are also there with him, but it was the first additive manufacturing machine was available in the market in the year of 1987. And the first manufacturing machine called as SLA. You might have heard about stereolithography. Stereolithography is the first additive manufacturing machine, and itself is the best additive manufacturing machine. That means, though the technology has been updated so far, but we could not able to get the same accuracy that whatever we are getting at stereolithography stage. So there are multiple names for the additive manufacturing also. There are multiple definitions. You might have heard about 3D printing. You might have heard, most of you might have heard with the name called 3D printing. Some people might have heard about rapid prototyping, rapid manufacturing, rapid product development, rapid technologies, digital manufacturing, solid freeform fabrication, 3D printing. These are all the synonyms for the additive manufacturing. But we are not supposed to call it as with those names. We are supposed to call it as additive manufacturing because there is a reason. I will tell you what is the reason is. So here you might know ASTM. Most of you might know ASTM. ASTM, American Society for Testing and Materials. So it's a standard organization. It's an organization which provides the dimensions for testing. Let's say I have a material. I just want to test the material up to what load it can able to bear. If I take this thick sample, it can bear more. If I take a thin sample, it can bear only very less. But which is the standard sample so that I can compare with other? Those kind of standards were provided by ASTM and it was universally acceptable. So ASTM has given this definition. I don't want to go it with in detail. But I will tell you one thing, that the additive manufacturing is quite opposite to the subtractive manufacturing. In subtractive manufacturing is nothing like machining operation. You used to do using lathe machines, milling machines. The process is quite opposite to it. Whereas in subtractive manufacturing, you use a tool to remove the unwanted material. Quite opposite to that is, I don't use a tool. I will not, instead of removing the material, I will add the material. That is what the basic definition for the additive manufacturing, and it was a layer by layer process. By virtue of it, it is doing it by layer way. So these are all the names that we are talking about, but it is more popular with the name called 3D printing. It is not supposed to be called with the name of 3D printing. So I'll tell you the reason. Okay, can you go further, please? Yeah, little more, please. Again, again, please. Please go forward. Please. Yeah, how many of you know this? You all know this, right? What happened? Any idea? Can anybody explain? Yeah, it's a simple thing that when Hanuma went to Ravana Darbar, he was not offered by a seat. He got little angry and then he created his own seat. How did he able to do that? If you might have seen in old movies, he created his chair with his tail. If you see it, it is not a single at a time manufacturing. He has done in layer by layer fashion. That too, if you see, he did not made it from the top to bottom. He did it from bottom to top. That is what the definition for additive manufacturing is. Basically, I want to show you a small video, but okay, you all know that, and I don't want to again waste the time. So now you go back to the previous slides. Previous slides, please. Go back again. So please wait. Yeah. Please. So most of the people used to say the definition for the additive manufacturing as per ASTM, it is a process of joining materials from a three-dimensional CAD data, usually layer upon a layer, and the process is quite opposite to the subtractive manufacturing technology. That is the definition. But that was the definition when it was invented. But the latest definition for the additive manufacturing is what you see that you can build. It is also called as visible. So what you see here that you can build. You just imagine something in your mind and make it as a CAD model in your computer-aided design model, CAD model that can be printable. That is what the latest definition. That itself gives whatever you imagine or whatever you see in the computer that you can able to build. That is the next definition for additive manufacturing. Please. As you all know, it's a process. First what we do is we create a CAD model in computer, and then there is a software called Slicer. Most of you might have using a slicer name called Cura. So it slices the CAD model and then it manufactures the component in layer by layer fashion to get the final component. If you see here, that is a CAD model, and there is beneath that there is a physical component which is manufactured. Physical component. So whatever you imagine that can be easily built using the additive manufacturing technology. Yeah, I'm not saying that it is not only the way that you are doing, but this is having a lot of advantages compared to other technologies, and it's the latest buzz in the present world. Next. So, as I told you earlier, there are multiple ways of, there are multiple technologies under the same additive manufacturing technology. If you see here, there are 7 categories. The first one is wet photopolymerization, then material jetting, binder jetting, and material extrusion technology, powder bed fusion, sheet lamination, and then direct energy deposition. There are multiple ways that you can, that means these are all the technologies. I am just giving you few numbers. There might be more than 150, 200 technologies that are presently available in the world. So if you see, one of the technology under the material jetting technology is 3D printing. Some people used to call it as under material jetting, some people mentions under it is a binder jetting technology, but it is only one technology under the subclassification of additive manufacturing. Somehow this got popularized, so everybody is calling all additive manufacturing technologies as 3D printing technologies. In fact, it is wrong. 3D printing is one category under the umbrella of 7 categories. And under one category, it's a subcategory. So somehow it got popularized. So most of you are Telugu guys, right? So you might have heard a name called Vennela Kishore, right? So why Vennela? Vennela Kishore is, it's not his surname, right? Vennela. First movie. Okay, very good. Chitram Sinu. First movie. Sakshi Rangarav. You might not know, but the senior faculty might know Sakshi Rangarav. Okay. So, and one popular movie, international movie, not international movie, it's an Indian movie to an international level. Surely you might have known. The villain name is You said Garbha Singh, you did not say Dharmendra, right? So why? He was so popular with that name, right? So generally, same in our regular life also. So to lift a vehicle, see, let's say a car got punctured, okay, deflated. I want to lift the car one side. What we use? We use jockey, right? What is the actual name? Screw jack. Screw jack we used to call it as jockey. Means it's in a regular day life we are calling it, but it's not actual name. Same like here also. So from now onwards, you please promise me that you don't call it as 3D printing. It's an additive manufacturing technology. As I know, I am telling to you, you please learn it and you tell to the others also. Don't call it as a 3D printing technology unless if it is comes under the material jetting technology or binder jetting technology, exclusively that particular technology. Otherwise, it's an additive manufacturing technology. Okay, please. So, if I, as a clear understanding, I might have told you this. Additive manufacturing is a process of joining materials from a three-dimensional CAD data, layer upon a layer, from bottom to top, and this process is quite opposite to the subtractive manufacturing. Most of the things, maybe Hanuma might have not used the CAD model, but the technology is the same, process is the same. So, who is the first inventor of additive manufacturing? Not Charles Hull, right? Not Charles Hull. So, mythological way, Hanuma is the first inventor of additive manufacturing. But we do not have that scripts that exactly he is the one who did it exactly. So, we always find, see, Ramasetu, if we say it's a mythological one. If NASA says it's an science. Right? Whatever we say, they feel it as a mythological one. But science involved in it. We are not, see, we are in a state that somebody should say that it is somebody that do not belongs to us, he should say that it is ours. Okay, so one of the technology I will be trying to explain you, there is a video here, if you try to play that video, that is a video, that is video actually, it's a video, it's not playing, every process is having a video. It's not? Okay. So I'll tell you a simple way. So in additive manufacturing also we have different ways of raw materials. See, for an example, if you are taking lathe machine, the raw material is a rod. From that you might make it as a bolt or some other component you will be manufacturing. The raw material is in the form of rod or in the form of billet. One way is the raw material solid. Other raw material here, for edit, there are in three ways we can manufacture the components from the raw material side. One is solid, you will be taking as a raw material. Second one is liquid, also you can take as a raw material. You just solidify the liquid and then you will be getting a part. And the third one is powder. So these three raw materials are these are all the only three raw materials which are available in the market to make a component using the additive manufacturing technology. Here, the resin, we call it as liquid, that is called as a photosensitive resin. Okay, what is the meaning of photo? Any idea? Not a picture, right? You are calling it as light, excellent. So the meaning of photo is nothing but a light, sensitive. What does it mean? Reactive, quickly reactive, right? So the resin which is shown here is quickly reactive with respect to the light. That means if I keep the resin here and under the light, not all the lights, there is a specified UV laser light which is available. If it is focused under that, and that liquid is converted into a solid. So the way of solidifying decides by a slicer. So I just want to show the videos, but it's not playing, I don't know why. But okay, fine. See here, in any process, whether it may be a wax photopolymerization, material jetting, binder jetting, or material extrusion, whatever may be the process. So you will be having a slicer. Slicer slices the CAD model. Have you heard a word called slicer? Slice. Regular life slice. Bread slices, very good. What do you do in that? You don't cut incline, right? Slice means you cut parallel to the base. That is what is a slice generally. So you take a CAD model, cut it parallel to the base, and individually manufacture each and every layer, one upon the previous one, to get the final component. Here also, the slicer generates a G code. That G code is a language between you and the machine, and then it acts according to that, and it manufactures the component in layer by layer fashion. I can give you this slides all to you, you can go through the videos, but there are certain ways to manufacture the component. That is about additive manufacturing. You can directly go to the, please, 7 slides you can slip, because there are 7 slides for 7 technologies. Yeah, it's also a video, it's not playing, but I don't know why. It's also a video. Okay, I'm skipping all 7 technologies, please. Yeah, please, now. Okay, here, you know the advantages of additive manufacturing because you don't use tools. For example, if I want to make a hole on a component in conventionally, you need a drill bit. Other than that, without any other tool, you will not be able to make a hole. Okay, specified hole. So, you need a specific tool. For an example, if I want a flat surface, I need a face mill cutter. If I need a thread surface, then I need a single point cutting tool. If I need a knurling operation, a knurl tool is available. That means for every specific operation you need a tool. But in additive manufacturing, we don't use any tools. The CAD itself is a final front end and back end for the additive manufacturing. So by using this, now where are we using this additive manufacturing? So many applications, you just name the area that is there already. It is also there in aerospace. Next please. Sir. He is playing with mobile. Hello. Defense. Okay. Next. Consumer electronics. Next, these are the commercial applications. Next, please. Next. Please go ahead. Okay, consumer goods. Yeah, automobile, architecture, educational, medical, molds. In multiple industries, the additive manufacturing has been used nowadays. We just name the area that already additive manufacturing has already tapped into in it. Means we are already using the benefits of additive manufacturing. First of all, why do we need to sir, one classic example I can tell you, that you might be feeling that additive manufacturing is having a size limitation, is one major limitation with the additive manufacturing. But actually it's not. That all depends upon how big the machine can be built. So this is a complete boat which was manufactured using additive manufacturing technology. So this, like that, see, it's a specific, I need a big part, I can build my own machine of big size, so that I can manufacture big components. Next please. So one important point to be noted here is, additive manufacturing is not actually more the awareness about the additive manufacturing in the industry is very, very less. There are multiple reasons for that. During the survey, it was found that 71% people were not knowing about additive manufacturing. That is the reason why they are not using it. 29% of people, they are not using additive manufacturing because of lack of confidence. That means, see, he might have tried one part, he might have failed, then he is keeping that entire technology aside. So it is not the actual one. So if you have the proper knowledge in the field of additive manufacturing, in the first attempt itself you can able to get the successful component. So the takeout from here is, we need to create awareness in the people. At the same time, we need to update our knowledge so that we can use additive manufacturing. Ultimately, we can able to get maximum benefits out of it. I'll tell you one example. See, I have taken earlier 1 kg of raw materials and that 20 bolts are made of manufacture. Will there be any wastage in the form of chips? Definitely yes, right? So, but that kind of wastage will not be there with the additive manufacturing. For an example, if I want to manufacture a gold component, will I be able to throw that scrap and all? Not even gold. So people are doing copper machining, the scraps of copper they are collecting it back because it's a costly material, precious material. So whenever you are working on precious materials like gold, silver, copper, in that situations the wastage should be very less. Then only you will be going to be economical, otherwise you will end up with a loss. Like see, I am taking maybe 1 kg of raw iron might be converted into 500 grams of bolts, but remaining a half kg is going to be wastage. But in case of additive manufacturing, in a survey it was found that 3 to 4% is the maximum wastage. That means maybe 30 to 40 grams of material is going to be wasted out of 1 kg of material. That too, that 3 to 4% is just for generation of support structures. That all we need to optimize. Please next slide. So these are all the advantages. You might have gone through some of the textbooks. These are all the advantages. Material efficiency. I might have told you earlier. The initial material is that much, and the final component is this. Huge amount of material is going to be wasted in the form of chips. Whereas in case of additive manufacturing, the wastage is almost zero. Almost zero. And it's a mass customization. See, how many of you are facing earbuds are not fitting into their ears? Most of the cases, right? Because they have only standard dimensions. So if it is fits with your ear, then you are lucky. Otherwise, you feel really uncomfortable. So mass customization. Simple, you might have known the wax. They will inject the wax in your ear. They will take the dimension and they scan it, reverse engineering. The same component can be 3D printed and the same will fit it too. Similarly, the functional integration. See, earlier to manufacture these kind of functional integrations, they do independently and assemble it. But a single component we can manufacture using additive manufacturing technology. Flow optimization. So the green color one is the drilled hole. Will it be possible a semi-circular hole? Will it be possible in conventional manufacturing? Not even. But in additive manufacturing it is possible. So even if you take a simple component or a complex component, the process is simple. So and tailor-made properties, the outside of the component should be cold and the inside, for example, flask. Okay, you take a flask. Outside, actually, the liquid inside is hot. The internal surface of the flask is hot, but outer surface of the flask is cold or normal temperature at the room temperature. The reason is you are using two different materials at both the sides. Instead of using two different materials, in a single material, you can have these kind of properties also. Tailor-made properties and part consolidation. Part consolidation means earlier, see, if you see functional integration, it's a single part. Means pre-assembly is already done. So when the pre-assembly is there, then you can avoid the assembly time, you can avoid the errors in assembly. These all are the major advantages with additive manufacturing. So some of the materials with additive manufacturing in metals, these are all popular materials. I am not saying that this is the only materials which are available for additive manufacturing. I am giving you some popular materials: titanium, Inconel, stainless steel, aluminium alloys, cobalt chrome, nickel alloys. Professor might have told about nickel based alloy only. That shape memory alloy is a nickel based alloy. So similarly, plastics, ABS, PLA, PC, polycarbonate, okay, HIPS material, PETG, PETG is also called PETG, TPU. TPU is tetrapolyurethane. See, simple, it's an elastic. You can put your hair band also. So flexible, you can make. There are some materials. Addition to that, you can also print chocolate, glass, concrete, biomedical materials, anything can also be possible. Please next slide. So that is about the basic introduction. But what is the present trend in additive manufacturing? We know in which industrial revolution we are. Are we in 3 or 4 or 2? Any idea? You might have heard about industrial revolutions, right? First industrial revolution, invention of. You might be bored with my lecture, sir. Okay, so presently we are about to finish the third industrial revolution. We are about to enter into the fourth industrial revolution. So the third industrial revolution is the major what I mean to say, the major objectives of the industrial revolution here is mass production with a specific materials. That was there already, but here mass production with a mass customization also. Let's say I want to generate 100 earbuds, that 100 are unique. That is called as a mass production with mass customization. Something like that is the third industrial revolution is already having, and some of the key points in third industrial revolution is reducing material wastage and connected to computers. Machine should be connected with the computers. These are some highlights. But if you go to the fourth industrial revolution, they used to call it as digital manufacturing or industrial era. So what we try to do here is connect the entire thing. Artificial intelligence you might have heard about. Connect the entire thing with the computer. So you connect your machine with the computer, and the human intervention should be always eliminated in the industry 4.0. So actually additive manufacturing falls in it, and there is a huge demand for the additive manufacturing either in material based or the research perspective wise also there is a huge demand. So if you see the picture here, could you please go back please. Image, yes please. So big data analytics, these are if you see these all things are one of the might be a specialization in industries which are buzzwords. Actually it's an industry 4.01, a specific era, maybe big data analytics, connecting it to computers, 3D printing technologies, cloud computing, cyber security, system integration, simulations, Internet of Things, robotics, augmented reality, AR, VR, virtual reality, mixed reality. These are the industry 4.0 major objectives. So one of the point which I would like to point out here is the future manufacturing is going to be the additive manufacturing, because conventional manufacturing is having its own limitations. So limitation either in terms of the dimensional accuracy or the accessibility, whatever it might be. But the same thing is not going to be reflected in 3D printing. So 3D printing or additive manufacturing, I supposed to call it as additive manufacturing, but everybody is calling us 3D printing, so I am also calling like that. So this is the major objective or future of the additive manufacturing. At the same time, I am not saying that additive manufacturing is the only best. Definitely it is also having some gaps. The gaps which are there here is the collaboration between the industry and academia, which is always missing in the field of additive manufacturing. So how can we actually, the points I would like to keep it here is the next slide please. Yeah, system integration and cyber implementation with industry and academia correlation with the additive manufacturing technology will give you the more opportunities. So please tell me who is going to be placed first? Is a computer guy or mechanical guy? Mechanical guy, eh? Then you should know about additive manufacturing. The trend outside is the computer guy is going to be placed first. Okay, the reason is the integration of industry with the academia is already well established. Whereas in the academia here, 3D printing we are just might be talking about the basic terms and all. But we are still having lot of gaps in academia as well as industry in terms of 3D printing and additive manufacturing. If that is filled, then you people will not be here, you will be in industries directly, straight away. So that is the major gap and needs required. That need might be related to the manufacturing or selecting of material, design perspectives, modeling, characterization, certification. It might be multiple, again, sub-classifications, but this is the major need. So why I was focusing here is, if you concentrate on this, you are going to be placed very quickly if you go out. So next slide please. So that's what I have, but I want to show you some videos, but it's not playing here. anyways, you can Google it. You will be able to get the videos, hundreds of videos on additive manufacturing. So, thank you for the giving this opportunity.
Thank you, sir. We are privileged to have you with us today, sir. Thank you. The presentation on shape memory alloys has been a very informative and inspired all of these students over here. And our audience should definitely know about your experience and expertise. Professor Amit Gupta, sir, professor at BITS Pilani, Hyderabad, he has received the prestigious Singapore Millennium Foundation Award and the Professor S. Venkateshwaran Faculty Excellence Award, recognized among the top 2% of scientists globally by Stanford University from 2019 to 2023. His research focuses on shape memory alloy, manufacturing process, optimization, and predictive modeling, with over 200 international publications and successful projects funded by BRNS, DST, and DRDO. Sir, here I'll always been encouraging students for their research work, and thank you so much, sir. Now, it's our privilege to express our gratitude and honor to our speakers, Professor Amit Kumar Gupta and Jayaprakash Sharma, sir, for gracing this occasion with their presence. May I request Radhika ma'am, Venkateshwara sir, to please felicitate Professor Amit Kumar Gupta sir and Jayaprakash Sharma sir, our keynote speakers. Jayaprakash sir, please. Once again, a round of applause for this invaluable presence and inspiring words. Thank you.
May I now request Dr. Pramod Kumar sir to please propose the vote of thanks.
Thank you. Good afternoon, one and all present here and attending on online mode. I, Dr. Pramod Kumar, Associate Professor of Mechanical Engineering and a member of IPSC, have the distinct privilege and honor of proposing vote of thanks on this inaugural ceremony of first International Conference on Advancements in Sustainable Energy, Materials and Manufacturing Technology. First and foremost, I would like to express our deepest gratitude to our keynote speakers, Professor Amit Kumar Gupta and Jayaprakash Sharma, for gracing this occasion and sharing your valuable insights and thoughts with us. Your presentations has truly enriched the spirit of this event, sir. A heartfelt thanks to our management team for their unwavering support and continuous encouragement, which have been instrumental in organizing this prestigious conference. We are deeply grateful for your trust and vision in promoting this academic excellence. We extend our sincere appreciation to our esteemed principal and conference chair, Dr. K. Srinivasarao Garu, for his leadership and constant motivation, which have guided the entire team in making this event possible. I would also like to express our heartfelt thanks to Vice Principal, Head Accuracy, Dr. V. Radhika Devi, Madam, for her timely suggestions and invaluable support in organizing this event, ensuring its smooth execution. I would like to thank this opportunity to extend our sincere thanks to Co-Chair Professor M. Venkateshwar Reddy sir and General Chair Dr. M.S.N. Gupta sir, whose dynamic leadership and support have been a driving force behind the successful organization of this conference. I would also like to extend a special thanks to our convener Dr. Y. Balaram for meticulous planning and dedication. Your efforts in overseeing every detail in this conference have ensured a smooth and successful start. A heartfelt thanks to the members of the various committees and faculty members of the Department of Mechanical Engineering, whose invaluable efforts in organizing different aspects of the conference and ensuring high academic standards have laid the foundation for a successful and impactful event. A special word of thanks to the students who have been tirelessly working behind the scenes. Your enthusiasm and hard work are greatly appreciated. You have truly been a backbone of this event. I would also like to thank Medha for your surprise presence here, and I hope our next international conference that is going to be held in the year 2025, you are going to take the entire control over the dais. A special thanks in advance to the session chairs and moderators who will be guiding the sessions. We are confident that with your support, the conference will foster meaningful exchanges of ideas and contribute to the success of this event. We also extend our sincere thanks to all the participants for contributing your valuable research work and sharing your knowledge with us. We look forward to learning from your insights throughout the upcoming sessions. Last but not the least, I would also like to acknowledge the essential support provided by the electricians and public address system team and all other who have contributed both directly and indirectly to the success of this inaugural ceremony. Your dedication and involvement, no matter how big or small, have played a significant role in making this a memorable occasion. Once again, thank you all for your presence and support. We look forward to the successful and enriching conference ahead. Thank you.
Thank you, sir. A small announcement to all the registered participants. Please make sure to visit the Center of Excellent Facilities provided by the Department of Mechanical and Aeronautical Engineering, which includes the NDT and welding machines along with the composite labs. And please make sure to collect the lunch tokens by 1:10 at the Center for Innovation and Entrepreneurship. The volunteers team will be available to guide you, and the presentations will be starting at 2:20 p.m. Thank you, everyone.